Okay, guys, today we're going to take a little bit of time. We're going to talk about chemical formulas and chemical equations. We're going to work in some of the stuff that we did earlier with acids and bases, and we're going to learn some new things about how we put entire chemical formulas, chemical equations together. So we're going to start with the two big kinds of chemical equations. And the first type, two major ones, like I said, the first one is called a word equation. And when you're dealing with a word equation, every single thing is written out in words. We don't use numbers. Like, for example, if the number 2 is part of the equation, we actually write out the word 2. We don't use our little things in parentheses like G for gas. We actually write the word out. So they can become quite lengthy. So again, a word equation where everything is written out, versus a formula equation, which is also called sometimes a skeleton equation. Not very often. I only am throwing that in there because I believe in your book they may actually call them skeleton equations, should anybody go there to look anything up. A formula equation is simply an equation that is the most efficient type of equation possible. It's where I'm using all chemical formulas, chemical symbols to represent everything that's taking place. So two major types, word equations versus a formula equation. Now, we're going to look at this and we're going to go through an example because you're going to have to be able to do these. So we're going to look at a formula equation versus a word equation. Here's a formula equation. I can take all of that information and I can write it in a sentence, basically. You just have to understand what all the symbols mean. That's the way I like to do it, as long as you understand it, because it's much quicker and it's much easier to do for you guys who don't like things that are lengthy. If I want to take that and I want to put it in a word equation, it becomes a little bit cumbersome. I would actually take this and I would write this out like this. 1 mole of solid sodium hydrogen carbonate reacts with 1 mole of aqueous hydrochloric acid to form, I could also say, that's representing this, I could also say yields, but to form works just as well. To form 1 mole I'm not sure exactly what just happened there. I apologize. 1 mole of aqueous sodium chloride plus 1 mole of liquid water and 1 mole of carbon dioxide gas. So look at the difference. This is all stuff you should be able to do based on what we've learned about ions and covalent compounds, ionic versus covalent. Knowing your charges, knowing metal plus non-metal, looking at all of those things to figure it out. So formula equation versus word equation. I will be, as part of your homework, giving you some formula equations that you have to make into word equations or vice versa. Okay, so formula versus word. Of course, if we're going to do this, we have to think a little bit about some of the symbols that you're going to have to know for chemical equations. And you guys already know some of these. So I'm just going to go through the list with you. of those that you should know. We've used this before in parentheses. Solid. So that tells me something is a solid. If you happen to see Cr in parentheses, that tells me it's a crystalline. Moving down the row, things we've had before. This tells me it's a gas. Have to know these for word equations. The AQ tells me something's aqueous. That means dissolved in water. If you don't know that, you better write it down. If we see a down arrow like that as part of the chemical equation, that tells me a solid precipitate was formed. If I see an up arrow at the end of an equation or within an equation, that tells me a gas was given off. And I'm just giving you the common ones. Obviously, we know this arrow. It means yields or forms. If I see this double arrow, that is called a reversible reaction. It means it can happen in both directions. So it's like equilibrium going back and forth. If I see something like this, the arrow with delta above it, or it could look like this. Heat. That's telling me that the reactants are heated. If I happen to see the arrow in the center with this, that tells me there was a temperature change. And moving right along here, if I see something like this, where it says triangle and then CAT, it tells me a catalyst was added. And you guys won't see that because we haven't really talked too much about catalysts or what we do with catalysts. Again, I apologize. It's super windy at my house and I'm kind of having the power flicker off and on a little bit, but I'm going to try to make my way through the rest of this video. Okay. The other thing that you're going to have to know as we start to write these chemical formulas and word equations and chemical equations are your different acids. We've talked about them already. First round are binary acids. Binary acids are made of just two elements. Always hydrogen plus a nonmetal. And I can always figure out what they are by looking at the equation. So obviously this hydro all the way down tells me it's an H. Then I have to look at the second part like we did previously to figure out what element. Fluoric, that tells me F for fluorine. Chloric tells me Cl for chlorine. Bromic tells me Br for bromine. Iodic tells me I for iodide. And S tells me S for sulfur. Then I have to think about, okay, what are the charges? Plus, all the way down. Then I can locate these on the periodic table if I don't remember. Fluorine is a halogen in group 17, so it's a negative. Chlorine's right there with it, a negative. Bromine, if you look, is a 1 negative. Iodine is a 1 negative. Sulfur is the only one that's a little bit different. When it forms an ion, it forms the ion sulfide, which has a 2 minus charge. So then I have to take those and I have to make them into their formulas. So I have HF for hydrofluoric acid, HCl for hydrochloric, HBr for hydrobromic, HI for hydroiodic, And that was easy because these were all 1-to-1 charges. Down here, I have a 2 negative to a 1 positive, which tells me, oh, I got to cancel out. I'm going to need 2 of these. So sulfuric or hydrosulfuric acid is actually H2S. Those are all binary acids because they're made of hydrogen plus a nonmetal, and they are neutral compounds. Okay, so that's binary. There are also acids that are called ternary. A ternary acid, you can think of it as having, we'll say, 3 or more elements. That should make sense, that ter there. Ter sometimes means 3, sometimes means 4 in these things, so we start with the 3. It's always hydrogen, and I want you to think of it as some type of polyatomic ion. And again, we have to make a neutral compound. So when I look at these, I've written some of them down for you. Nitric, sulfuric, phosphoric, and carbonic. These all end in an ic. And acetic, I forgot I put that one on there. All end in an ic. And if you remember previously, when we had an ion that ended in ATE, when it becomes an acid, we replace that with ic or IC. So I have to think about these. I know all of them are going to have hydrogen involved in their formula. That's a giveaway. Then I have to think, okay, those are all my cations. What is my anion going to be? So nitric, if I replace this ic with an 8, that tells me nitrate. And my formula for nitrate is NO3-. If you don't remember that, you can look at your polyatomic ion cards. No big deal. You're going to have those. If I look at sulfuric, okay, ic, replace it with 8. That tells me sulfate, which is SO4, 2-. Phosphoric, replace my ic with an 8, is phosphate, which is PO4, 3-. Carbonic, replace the ic with an 8, and I get carbonate, which is CO3-. And last, acetic, if I replace the ic with an 8, I get acetate, which is the C2H3O2. It's one of the cards that you have written 2 different ways. So let's remember all my hydrogens are positive. And my goal now is to take these and to make a neutral compound that I understand, because of its ending, is an acid. So nitric acid, I'm working with hydrogen and nitrate. A +1 and a -1 cancel each other out. So nitric acid is just HNO3. Sulfuric, I know I have hydrogen plus my sulfate. This is a 2-. This is only a 1+. Tells me I need another one of these to cancel this out. So that becomes H2SO4. Phosphoric, I've got a 1+ to a 3-. Tells me I need 2 more over here. H3PO4. Carbonic, these are the easy ones. A + to a -, I don't have to do anything. I just carry it over. HCO3. And lastly, acetic acid. Acetic acid is basically what vinegar is that you buy at the grocery store. Just watered down acetic acid, like really watered down acetic acid. Pure acetic acid will like burn the hair right out of your nose. Anyhow, I've got a 1+ to a 1-, HC2H3O2. Those are the only binary and ternary acids that I'm going to hold you responsible for. If we were at school, I had a whole bunch of really cool labs to do to figure this out, but we're not. And so we're just going to move right along with it. All right, so those are my ternary acids. So now you have binary acids, ternary acids, and the last thing we have to think about is being able in these equations to pick out a base. And we've been over this before. I just wanted to review it a little bit. A base is a metal plus the hydroxide ion. And remember, the hydroxide ion is OH-. So anytime you see any formula with this OH- in it, you know it's a base. And remember, a metal can be group 1 through clear to the other side of the periodic table, clear through to our other metals and our non-metals, right where they butt up and we get that stair step. So remember, those move all the way across the periodic table. So we start them with the alkali metals, clear through other metals. So it's a big chunk on your periodic table. You should have your periodic table, your colored one, home with you, so it's easy to figure out metals versus non-metals. I'll just talk about a couple like really simple ones quickly. Let's talk about potassium. We'll use that one. Potassium hydroxide. I know it's a base because it has hydroxide. So I know hydroxide is OH minus. If I go to my periodic table and I find potassium, I know it's K plus. So this would just be KOH. Think about something a little bit differently. Let's try zinc hydroxide. Zinc is an ion, monatomic ion with a charge of Zn, 2 plus, and I've got hydroxide, which is just a 1 minus, means I'm going to need another one. So zinc hydroxide would be ZnOH 2 times. So I'm not going to do a whole bunch of these. Let's say maybe I give you iron 3 hydroxide. Again, you should go, oh, that's a base. It has hydroxide on it. This is one of the easy ones. I don't even have to go to my periodic table because it tells me in the stock system 3. I know it's a cation with a 3 plus charge. So Fe3 plus OH minus. I want a neutral compound. If this is a 3 plus, this needs to be a 3 minus. We've done this tons and tons of times. That tells me I need 3 of these. So I need FeOH 3 times. Okay, so that should give you a little bit of clarity on acids and bases. And obviously when you work on this stuff, you'll have your notes, so it won't be too terrible to move through. When I look at these chemical equations, I have to look at the type of formulas that are found in them. And this is the last thing I'm going to go over in this video. So let's talk about, if I can get the papers apart, the types of formulas found within a chemical equation. And there are going to be a lot of them. And there are some that we're going to work with. We're going to do some math with them. And we'll be able to figure out exactly what they are given certain percentages. And we're going to work on that in the next time. But the first type that you need to think about is called a molecular formula. A molecular formula is found within a chemical equation, just like all of these formulas I'm going to go over. Molecular formula always deals with covalent compounds. Compounds that are sharing electrons. Remember, covalent tells you that we are sharing electrons. Tells you exactly what's there and exactly how many of each. So a simple molecular formula would be something like this. CH4, which happens to equal methane. It's telling me there's 1 carbon and 4 hydrogen equal 1 methane. So that's a molecular formula. Notice this is a covalent compound because both of these are non-metals. Remember, a covalent compound is equal to a non-metal plus a non-metal. So covalent, 2 non-metals. That's a molecular formula. The next type of formula is a formula unit. Formula unit we're going to talk more about next time because sometimes these are a little difficult to understand for people. A formula unit is what we call an ionic compound. It's called a formula unit because it tells us exactly what's present, exactly how many of each, and it's always in its most reduced form. It's in its most reduced form because it's ionic and it is a neutral compound. So whenever I have a neutral ionic compound, it's always in its most reduced form and it's called a formula unit. So I can pick anything for an example of that. Let's think about a couple of our ionic compounds. I'll start with, let's say, a monatomic element, and we'll start with, let's start with calcium, which is Ca2+, and we'll say that it's going to hook up with chlorine. Chlorine, we know, becomes chloride Cl-. When I put those together, I've got CaCl2. It's an ionic compound. It's also called a formula unit. It's its most reduced form. I can't make this any more reduced than what it already is. So it's a formula unit. And if you have an ionic compound in a chemical equation, that ionic compound is called the formula unit of the ionic compound. Okay. Third type is a structural formula. Structural formula is a little bit different. You can have a structural formula that can either be a formula unit, or it can be a molecular formula. Either one. This would be a covalent. This would be if I'm dealing with an ionic compound. So let's look at these and what they would look like. Let's say I'll work with my ionic first, and I use CaCl2. Then I'll work with my molecular, and I believe for that I used CH4. So if I have a structural formula, it's actually a picture. It'll look like this: CaCl, I can look at it, I can see how they're bonded and exactly what's there. My molecular formula, I use my methane, so I've got a C and my 4 H's. So that would be my structural formula of my molecular compound, my molecular covalent compound, methane. 1 carbon, 4 hydrogen. So they both show us what's there, how many, how bonded. So how many of each, how they're bonded, what it looks like. It's a picture, sort of a picture. All right. The next kind that we're going to look at is called a ball and stick formula, or a 3D representation. So it's like a model. If we were at school, I have all kinds of models that we were going to work with, and we were going to build some of these different compounds. So it's a 3D model, it's a ball and stick model, all of those things work. They end up being actually 3-dimensional representations. So let's look at my CaCl2 versus my CH4, and this is where you start to see the pictures and the different colors. So I'm going to look at this one, and my Ca is going to be represented by this blue ball. I'll show my bonds, and my Cl, 2 of them represented by the green. Obviously, it would be a little bit different if we had the actual pieces here to work with. CH4, I'll make my carbon blue, color that in, show as best I can each of my H's. We'll make my H's pink. And so using the formula, I can figure out what's what, but it's actually a 3-dimensional model. I printed off a picture of what the methane, this is actually the CH4, what it would look like if we were building them, the 3-dimensional models, versus me just trying to draw them on paper. And then the very last one that I want to go over, and we'll be done, will take us into the next time, is called an empirical formula. And this is the one that allows us to do math and some different things. An empirical formula tells what elements are there, but they're represented in their simplest ratio. Empirical formulas only really apply to covalent compounds when we work with them, because ionic compounds are always in their simplest form, because their goal is to be neutral when they transfer electrons. So if I have an ionic compound, it is an empirical formula. If I have a covalent compound, I have to stop and see, Is this most reduced? Is this empirical? Or is this the molecular formula? And the next time we meet, we're going to talk about the difference between those two. Thanks. Have a good day.